Hey, welcome to Build 2. This is the channel where we dive deep and go super nerdy on math and stuff that would never catch any attention on YouTube. This is for the shower power video. I splurged on one of these Remarkables and I have not been able to put the thing down. They're not sponsoring me or anything, but I used to go through stacks of engineering pads and now it's all in this one device. So we're going to use this real quick to go into some basic physics of meters and units and kilograms and that kind of stuff. Go through a brief explanation of that, and then I'm actually gonna take you through the video, and we're just gonna pause at each of the calculation spots and I'll walk you through everything I did based on the units, and we'll see how that works out. Sorry for the mess on the bench. We've got about 3 projects going on at once. My son and I have been working on our custom H-bridge controller for something special for a future video, and so it's a bit of a mess, but this is what electronics benches look like. If you go to any professional electrical engineer, electronics lab, this is what it is. So I'm just gonna kind of shove things to the side. We're gonna lay out the Remarkable, get a camera looking down on it, and go into that right now. Like I repeatedly say in the videos, everything is easier in metric, and here is why. If you want to look at a unit of length, it's in meters. You have, I'm just pretend I'm left-handed here for a second. Looking for mass, it's in kilograms, and looking at time, of course, in seconds. Now, if we just focus on those top 3 things, you can do just about everything you want to with it. So, for instance, let's look at velocity is meters per second. You know, it's distance over time. So in metrics, yeah, meters per second. And then acceleration, this meters per second squared, or like my dad used to say, meters per second, whichever one makes more sense to your brain. I think of acceleration as it's changing velocity. So if you're just going down the highway at, here in the States, it's going to be miles per hour, or it's going to be kilometers per hour over in Europe, depending on where you're at. If you're going at a constant speed, if you start to accelerate, the harder that you accelerate is a greater change in velocity. So when velocity is meters per second, the meters per second change per second, hence the seconds squared. And if you don't like thinking of driving down the highway or a drag racer taking off, you can think of gravity jumping out of a plane. My wife was crazy enough to jump out of a plane at one point. The 9.8 meters per second squared is the acceleration you experience due to gravity until you run into wind resistance, that whole terminal velocity. Eventually, if there was no atmosphere, you wouldn't hit a steady speed, but here on Earth you do. And I forget what is it, like 11 meters per second, I think it is for a human body falling. Anyway, gravity is 9.8 meters per second squared. That is the rate that you accelerate at when you're falling or any object is falling in free fall. And that is another number that gets burned into your brain in physics and engineering. So moving on to the classic, I don't know if you remember this or not, if you've heard it before, F equals ma, force equals mass times acceleration. And that's how we start taking this stuff in and coming up with a force. Now, okay, force is kilograms meters per second squared, huh? Well, if force is mass times acceleration, what did we say our mass was? Mass was kilograms, and acceleration is in meters per second squared. So if we multiply mass times acceleration, we get kilograms times meters per second squared. That may not make a lot of sense to you. That may sound like a complete foreign language, but that is something, if you're going to go into physics or go into engineering, you need to burn that into your brain, that kilogram meters per second squared is force, and that is what we call newtons. So anytime you see a newton, just automatically, it's kilogram meters per second squared. I have used this countless times as an engineer when I need to go back to the basics to calculate something. What is happening to my tongue? Now, let's go from force to energy. So if we're thinking of, I need a block of metal. Just a second. here we go. Can you see this? Yes, you can. So this thing has mass to it. And the mass is, if this thing was floating in outer space, like an object orbiting the Earth, maybe you're on the space station and you're going to throw this out into space, it has mass to it. There may not be any gravity to give it force, but it has, and it's floating around, but it has inertia. It takes something to get it to get going. And that's what mass is. Force doesn't come into play until you have gravity associated with it or an acceleration. So the harder you throw this thing, I guess, is the acceleration you're going to give it. So the higher F equals ma, the higher the mass, the higher the acceleration, the more force it's going to take to get it there. Now here on Earth, we tend to think of the force as it's sitting on a tabletop with the, again, we can measure the mass. We're really measuring the weight, but we can get the mass in kilograms times our 9.8 meters per second squared, and there's our force of it sitting on the tabletop. Now, if we're going to talk about energy or work, that is the work that it takes to move it from point A to point B. So I am going to give it a force that is something less than the weight of it, that I'm going to push it a distance. And so the force times distance is our work or our energy. And that's where we end up with this. If the force is in newtons and the distance is in meters, then we end up with Newton meters for our work, which is the unit of joules. So in the rain gutter video, the first rain gutter video, I talked about work, and rather than having a weight that we pushed over a certain distance, we were lifting it. So I was picking up a jug a certain height. So that's where you have, it's much easier to take the weight of that jug, which it was full of water, so it'd be 8 pounds, whatever kilograms that is, and lifting it over a height. There you also have newtons times meters, that is a certain amount of energy. Now how fast, the rate that you are consuming your energy is, so what we had, force was kilograms meters per second squared, newtons, and energy is force times distance. So we could scrawl out this kilogram meters per second squared times meters, or okay, Newton meters or joules for short. Power is how, again, we can go through this whole kilogram meters per second squared times meters per second, or it's Newton meters per second or joules per second. So eventually you get to the point where you're only speaking in newtons, joules, and then watts is our power. But every time you start working with these and you have to do a fancy calculation, it's really nice to know when somebody tells you watts, you can go, oh, that's joules per second, which is Newton meters per second, which is, and when you break it back down to these basic terms, you almost don't even need equations anymore. You can just work through your units and make sure everything comes out. The one that I added down here at the bottom that I was going to leave out was pressure, because we talked about pascals, and it is force per unit area. You think about the air inside of a piston pushing on a certain area, and you know, I was raised in PSI, pounds per square inch. But instead of pounds over square inches, the metric form is newtons per meters squared, which works a lot better with all of this than trying to figure out pounds per square inch. It's just a, metric is just better. Now, number one, your answer, when you work through all this stuff, your answer better be in the right units or you forgot something. And I did that throughout the video. We're about to talk about that. And then first principles, when people reach out to me because of this channel and hey, look at this crazy place I found energy. And they're like, oh, you'll finally invest in my thing, or you can help me with my invention. And I don't mean, you know, they're good intentioned, but I have to disappoint them in that I can do math. I can take these things and add it all up and say, hey, look, the total amount of energy that's available is X amount of watts, and that's nowhere near what you are claiming that your device or your thing, your energy capture thing, has available. So sorry, if the math with no resistance is giving me some number less than what you're claiming, then what you're claiming is incorrect, or you are aware of some form of physics that that we haven't discovered yet, which is the odds of that are something slightly less than zero. So it's a good way, knowing this stuff is a good way to avoid getting caught up in the latest wind power thing. This thing is going to generate so much energy. Armed with this stuff, let's go through the video. Me in the shower, something I never thought would be on the internet, but there it is. Okay, going to 52 seconds in. These are the original calculations that I did on the original rain gutter video. So we had a tube here that we were stacking up water in that was going to build up some pressure, and then I had a calculated flow rate, what a quote-unquote moderate rainfall rate would be. I calculated that in gallons per minute because that's what I usually work with here in the States, and I think like 40% of the audience of this channel is US based, so okay, using gallons. But knowing it would be easier in metric, I converted it to liters per second. And then, like I've said many times, the instructors, the professors in engineering school burned into our brains that rho GH is how they said it. And rho was density, G was gravity, H is the height. Rho GH is your pressure. And if I list all these units out, you can look at it in a row. The liters per second, the 1.8 meters, the kilograms per liter is the density of the water. You could round that up to 1 kilogram per liter, but at normal temperatures, this is what it is. And then gravity, meters per second squared. Multiply all that out. If you watch that pizza video I did on the math that engineers use most, you know that liters over liters, anything over itself is equal to 1, and it can just go away in your equation. So the liters are gone. And what do we have here? Kilograms, meters per second squared, which we know is a Newton. So we're going to turn all that into a Newton. We've got a meter, so we've got Newton meters, and then seconds over here in the denominator. So we have Newton meters per second, and we know that Newton meters are joules, and that joules per second is a watt. So we just multiply, once you have your units figured out, you can just multiply all those numbers, grab your calculator, and it came out to 2.08, and we knew for sure that we had no more than 2 watts, and no ram pump, no amount of trickery was going to increase this number unless we like hooked up some solar panels and got a pump out or something. This is the maximum amount of energy you have available. Nobody's going to fool you into thinking that they're going to get 100 watts off of their rain gutters, at least since I have done these videos and showed everyone how little it is. So let's see, 157 is what we're going to now. Yeah, so here I did not know. I didn't look up any of this stuff in the physics book. I just knew from the basics that, all right, this chunk here is going to represent pressure. And I could have cheated and backwards calculated what the equivalent meters would be for my 80 psi height. And I guess I could have plugged that in and figured it out. But it's like, no, I'm trying to teach this stuff. Let's replace pressure with pascals. We know pascals are the metric unit for pressure, but then wait a minute, pascals we know are newtons per meter squared, and I went to try to calculate that through, and I had liters and meters, and it's like, what am I going to do? This isn't going to work. Oh, okay, to make this work, I had to cancel out, turn the liters into meters squared, and that's the beautiful thing about the metric system. Liters are volume, meters cubed are volume, and so 1,000 liters is 1 meter cubed. Cancel out the liters, and now I've got this tiny little number in meters cubed per second, and then we were able to multiply that through times this huge number, cross out the pascals and put newtons per meter squared, and we end up with the units all work through to watts into the same Newton meters per second. And that's where we get our number for 70 watts. Jumping to 427. All right, Bernoulli, and you take fluid mechanics in college and they will just burn this equation. Every problem, I want to say every problem that we did in fluid mechanics started with this equation. You basically wrote this at the top of your paper. And it is ugly, but every single time you use it, you're canceling part of it out. You're looking for excuses to get rid of it. and this is no exception. We know there are pipes in the wall that are feeding this, but if we assume that this is like a giant above ground swimming pool and we just drilled a hole in the side of it, we can make a lot of assumptions. For instance, the velocity, this V1, well, actually, let's go back to the equation here for a second and not cross everything out. P1 is the pressure. We've got pressure on both sides. So the equal sign is kind of like the side of the swimming pool, and P1 is all the ones are inside the swimming pool. The twos are the jet of water coming out. And so we have a pressure term, we have a height term. So if this was just a long garden hose that was coming from maybe an upper story to a lower story, maybe I could do that for the pump storage video. And the H1 would be the one height and the H2 would be the other height, which rho GH would give you a new pressure that would add to the existing pressure. And then this V here is a velocity. So we've got a sort of a potential energy bit, and you've got sort of a kinetic energy bit where it's the moving water has energy associated with it. There you go, and you've got it on both sides of the equation. But if we're considering this like a above ground swimming pool that we drilled a hole in the side, the velocity inside the swimming pool is nothing. It's just sitting there. It's ginormous. You consider it infinite. So inside the swimming pool, there is no velocity. So the V1 goes to zero. And because it's zero, this whole term just disappears. And then the height, when I first drew this out, I was okay, I've got the jet coming out here and the water's coming in up there. And that height is so negligible, it might as well be zero. But if you're just looking at the jet coming out of the side of a pool, then it is zero. And this H1 and that H2, these things are equal. If you subtract both sides by one of them, then they just go away. And then your P2 is the pressure of this, the atmosphere where the jet comes out. And since we're not in outer space taking a shower, our zero pressure is our atmospheric pressure. So yes, there is some pressure here in absolute value, but we're just going to use gauge pressure, and the gauge pressure here would be zero. So the P2 goes away. And what we are left with, if we just step forward, is the P1 is still there. We have an equation for the pressure of P1, and rho, the density of the water, times the velocity of the jet, squared divided by 2. The only unknown here is the velocity of that jet, so we just rearrange it to get our V2 by taking the square root to get rid of the square on the V. Let's see, there's our answer, 33 meters per second. But we plug in our pressure in pascals, and our density, I just rounded it off to the 1,000 kilograms per meter cubed. And so here is our pascals of newtons per meter squared, and then we've got this density of kilograms per meter cubed gets inverted because it's on the denominator. What is it? Dividing by something is the same thing as multiplying by its reciprocal, they used to say. And this is where our newtons, knowing what a newton is, really helps here, because that newton is a kilogram meter per second squared. So we now have a kilogram on top and a kilogram on the bottom. Those go away. We have a meter, an extra meter now, so that turns this into meters to the fourth and a meter squared. So the meter squared goes away and leaves us with a meter squared on the top. Let's see, kilograms, meters per second squared. So now the second square goes on the bottom. And now there's a moment of panic here where we say, wait a minute, I'm looking for a velocity, and I have meters squared over seconds squared. But, oh, that's right, we are underneath a square root sign. So both of these squares go away. We're left with meters per second. And man, does that bolster your confidence when you can just look and all this stuff that you did, the units come out to exactly what you were looking for with the velocity. It's in meters per second. Hallelujah. If it came out to anything else, we did something wrong. Maybe our numbers were right, and we didn't carry our units through properly, but that's your best indicator to go back and see if your answer was correct. It's what makes the metric system beautiful. All right, what's our next timestamp? 4:56. Ah, yes, the flow rate of our nozzle. If you remember in high school, or maybe you're just getting to high school or in high school now, math teacher would have you calculate the area of a circle, and I know my math teacher never told us why. They just said, here's the area of a circle. It wasn't until I got to engineering school that I realized what it was for. So if you have that area and you know the velocity of the water, that gives you your flow rate. You give this area of the circle times the velocity. We know the velocity. We don't know the diameter. So we can just rearrange this. D equals 2, the 4 comes outside of the square root sign. D squared, square root of that. And so there's our formula, plug everything in, units cancel out, and we're left with millimeters. I don't have any millimeter drill bits. All of my drill bits are in inches, so I converted it to 0.086 inches, or 86 thousandths, as we would say here. Let's see, 544, but that did not, as if you watch the video, that did not come out to the proper flow rate. It was too low, and so we threw this pressure gauge on and realized, oh, we were actually closer to, I just picked 50 psi and recalculated with that new pressure and got a much smaller, a larger nozzle size of this 0.097 inches. And because I didn't calculate in any friction or how rough the inside of the walls of the nozzle are, maybe I could have polished it and improved the finish and improved the flow. But this 0.097, I ended up having to take it up to 0.110, so roughly 10% bigger than what I calculated. And that's just how, hey, if you do your calculations with no friction, what you actually get in the real world is going to be something less. And that's a good thing to know, good thing to expect. Quick note on these voltage converters. These things are really cool. 1, 2, 3. I wish I had these when I was a kid, because they allow you to take any DC voltage that you have, almost any DC voltage that you have, and convert it into the thing that you want. So there's boost and buck. Boost is the one that goes up, that raises the voltage that you have. Buck reduces it. It's much more efficient. That's what we have here, are buck converters that were reducing the voltage down. Turns out the voltage coming in was way too high without rewiring the generator. But yeah, these things are super cheap. You can get them by the bag off of Amazon or any electronics supply. They are a great thing to have around for any electronics project. Let's get to our three-phase stuff. Yeah, so three-phase power is what industry runs on. You go look at the hydroelectric dams, nuclear, coal-fired, whatever it is. They're all spinning some sort of generator that has 3 phases built into it, and it's way more efficient that way. It runs smoother, it's all good. But homes don't typically have 3-phase, and I've been shopping for lathes trying to see if I want to get an upgrade to my single-phase lathe, and you'll find one at a good price and you realize, oh, that's a 3-phase machine. I'm not going to be able to run that at my house without some sort of phase converter. But when you look at power poles, all the way up on the top, you'll see these 3 big wires that are kept way far away from each other, because that's where the power is. And each of those represent the phases that were coming from the power station, whatever type power station it is. And so, yeah, it's just kind of cool to appreciate that 3-phase. And this truly was the first time that I'd ever done any kind of delta, or I'd read about it a number of times, the delta versus the Y wiring, and I really did just get my son set up on that and go, here you go, figure it out. And I checked his work, it looked good, and then yeah, it functioned. I think this generator just isn't what's optimal. You know, it wasn't built to be used for a shower. Go figure. If we're going to follow this up, if there's enough interest, we'll follow it up with a different type of generator and see how much more power we can get out of it. So there you have it. Hopefully that was helpful to somebody. I know that would have been very helpful to me in high school when I really wanted to learn physics and it just wasn't clicking for me. I was that kid in a small town that didn't have access to this information, and it would have been really nice to have somebody explaining it and showing it in a sort of practical example. If you haven't already, subscribe to this channel and to the larger channel. Tell somebody about it. I want to have a positive impact on as much of the population as possible, and that only happens when we share this and get the word out. All right, I will see you in the next video. Thanks for watching.